Okay, we are finishing up. We're doing the last part of the differential amplifier for lab 16. And we just replaced the tail resistor in this differential amplifier with a current source. And the reason we did that is we want to reduce the common mode gain even more. So we have this R tail factor, actually 2 times R tail factor, in the denominator here for the common mode gain. It does not appear in the differential gain. And we want to make that R tail value as large as possible. And a current source is actually a pretty convenient way to make that R tail value huge. So R tail in our EE board version of this circuit was 10 kilo ohms before, but now we're able to make our tail appear as if it were 2 mega ohms roughly. And if you put a 2 mega ohm resistor here, remember that the whole purpose of the tail resistor was to flow a constant, little less than a milliamp. It was like well, actually, with the R tail, it really was pretty close to 0.8 of a milliamp. Because we had this was about a volt below zero, so we had about 8 volts, and we had about 10 kilo ohms, so it was roughly 0.8 of a milliamp flowing through the tail resistor, so then half went through this side and half went through this side. So we said, okay, let's try replacing that with a current source. And you say, well, why would you want to replace it with a current source? So an ideal current source has, okay, well, first of all, remember an ideal voltage source has 0 output resistance, right? So Thevenin resistance, output resistance. So the output resistance, also known as the source resistance, also known as the Thevenin resistance of an ideal voltage source is 0. The output resistance, also known as the source resistance, also known as the Norton resistance of an ideal current source is infinity. So an ideal voltage source has dV out with respect to dI out is tiny. Ideally 0. An ideal current source, ideal current source has dI out with respect to dV out. In other words, it outputs the same current right, this is small. You want it to output the same current even if the voltage across the load changes. So it may, here, for example, you might have an ideal current source and then some load, and that's your circuit. And the ideal current source would supply the same current whether you make the load big or small. Of course, it's easiest if you make the load small, but if you make the load big, it would, for an ideal current source, it would still work. Okay, so that says that this slope, the change in the output current with respect to the output voltage is small. That means, turn it upside down, this is a reciprocal resistance. If you put it in terms of resistance, the change in the output voltage with respect to the output current is large. That's known as the output resistance or the source resistance, or for a current source, it's called the Norton resistance so Norton resistance for a current source is like the Thevenin resistance for a voltage source. You draw it in a different way. So a good current source has a very large source resistance, has a very large output resistance. And it turns out that when you make a current source with a bipolar junction transistor, for reasonable choices of parameters, you can get an output resistance for that current source on the order of mega ohms. we can measure that in circuit. In this course, the only way we know how to do that is actually to measure it in Circuit Lab. I actually found the notes for a Georgia Tech electronics course, and it gave an incredibly complicated formula for the output resistance of a current source that looks just like this one. And I simplified their very complicated formula to try to just bring out the most important terms. And this is what I got, simplifying their formula. Let me just put this in terms that are a little more typical for the current source we would draw. So we would have, there would be like some kind of R1, some kind of R2, and these would go to fixed voltage sources, whatever they are. Maybe you call that V2, call that V1. In this case it's ground and minus 9 volts, but it could be something else depending on what you're doing. And then you have a transistor here, and then here's the load. And then the load's going up to some fixed voltage. And then we have an emitter resistor here, and then this is going down to some fixed voltage. Might as well be the same voltage as this. So then you say, what is, and then this is the collector current for this transistor, since this is, the collector, the base, the emitter here. And you might want to, and then of course this voltage, if you look at the voltage here, if you look at the voltage here, this is the collector voltage. So you might want to say, what is the change in collector voltage with respect to collector current? And you want this to be big because really what you want is the reciprocal of this to be small. So it turns out that you can write down an expression that's the early voltage, which is a parameter of the transistor. It's about 75 volts for the 2N3904 transistor. And then VCE, that's the collector emitter voltage for this transistor. And then IC, the collector current for this. That's basically the current that you want your current source to flow. And then this is the emitter resistor here. See, I put it in terms of this circuit, but it's probably useful to write it in terms that are more applicable to another current source you might build sometime. This is the little RE for this transistor, right? So that's like the transistor behaves as if it had like a little, when it's, it's as if it has like a little emitter, a little resistor inside the emitter there. And then this is plus R1 parallel R2 divided by beta. So this apparently is like the resistance you see looking up into the emitter. So you see this little RE, and then you also see what's behind the base, but divided by a factor of beta. I think in the original expression it was beta plus 1. I treated beta as big enough that beta and beta plus 1 are the same thing. And there are a couple other things that are small that I neglected. Like there's a small number, things that are really small divided by beta I just neglected. So I only put big things divided by beta. Okay. So then if we plug in numbers for this scenario here, this is, so for the 2N3904, we have the early voltage is 75 volts, and we have beta is about 150. I think it might be 140. Well, let's say it's 150. And, okay, and then we have RE was 1 kilo ohm. So let's call this here 75 volts plus, and VCE was about 8 volts, so there's 8 volts. And then this was a little less than a milliamp, so we'll say 0.8 milliamps. That's an M, milliamp. And then this was a kilo ohm. And then, what's little re? Little re is 25 millivolts divided by the collector current. So it's 25 ohms divided by 0.8. And 20, I think that's like 0.33 or something. So 25 divided by 0.8. That's like 31 ohms. Plus, okay, R1 parallel R2. In this case, it's 10K parallel 2K, which you know is about 2K. So 2 times 10 divided by 12. That's 1.7 kilo ohms. Okay, so this is 1.7 kilo ohms divided by beta, which is 150. And what do we get? Let's see what we get. We get 75 plus 8 divided by 0.8. So that term is 104, basically. This is 104 ohms. Oh no, it's 104 kilo ohms, right? Yeah. So I think this number, just this term by itself, is I think roughly what you would get if the emitter were grounded here. So 104 kilo ohms. But then there's actually a feedback mechanism. So it turns out, see, if the current starts to get too big, then the emitter, because of the presence of this emitter resistor, if the current starts to creep up, then the emitter voltage creeps up a little bit, and that clamps down a little bit on VBE, which has the effect of reducing the collector current. So that's feedback. Or if the current gets too small, then the emitter voltage goes down, because this current goes down, so the emitter voltage goes, current goes down, emitter voltage goes down. So then VBE is bigger, so then that increases the collector voltage. So it's a feedback mechanism. And the effect of that feedback mechanism is to make this slope, which is the kind of this early effect of the transistor, smaller by a factor of roughly this emitter resistor divided by the resistance that you see looking up into the emitter. So what do we have here? We have 1 kilo ohm divided by 1.7K divided by 150. 1700 divided by 150 is 11.33. And if you take that and you add 31 to it, then you get 42 ohms. Okay, and what is that? So you have 104 times 1,000 over 42. So you get about 2.5 mega ohms. Okay, and I think, yeah, I think I rounded it down to 2, but anyway, yeah. Something on the order of 2 mega ohms. And I think you can check that in Circuit Lab. That'd be kind of interesting to check in Circuit Lab. For this exact circuit, I think I actually measured in Circuit Lab something like 3 mega ohms for the version we use in the 15-volt version of this circuit. Okay, so what that tells you is that the dynamic resistance of this current source is like about 2 mega ohms. So that says as you change the collector voltage, which is this point here, which is what we were calling Vx in the previous video. So as Vx goes back and forth, let's see. I hesitate to draw a vertical axis here. Actually, I guess it's always negative, so maybe we'll draw a funny set of axes here. So, I just said we'd draw a funny set of axes. So let's draw, here's the collector current, which is the current of our current source. And here is the collector voltage. And so it seems like normally this is close to 0. So when this is close to 0, we get our 0.8 milliamps. So I guess this is like 0.8 milliamps. Okay. And then So this is like VC is around 0. But then the point is, which way does it go? So then it seems like if VC goes up, then IC goes up a little bit, I think. Yeah, so I think it has a slope that's a little bit like this. So an ideal current source would have absolutely 0 slope. So this slope is something like this slope is like the reciprocal. Oh, right. Okay, here we go. So the reciprocal of this slope is something like 2 mega ohms. So you want it, so you want the reciprocal of this slope to be a small number. So you want this number to be a big number. So anyway, so the cool thing about using a current source instead of a resistor, see, if you wanted to do this with a single resistor, and suppose you want a 2 mega ohm resistor. So if you have a 2 mega ohm resistor with, let's say this is approximately 1 milliamp flowing through it, then I times R is what, like 2,000 volts. So you would have to go from 0 volts down to minus 2,000 volts. You would need a 2,000 volt power supply to get that good an effective tail resistance if you were going to use a resistor. But see, the neat thing, because with a resistor, the IV curve goes through 0. When you have 0 current through the resistor, you have 0 voltage across the resistor. So I guess that would mean, well, actually in this case, what that would mean is if you had 0 current through the resistor, this voltage would be minus 9 volts. Anyway, the neat thing about the current source is that you can have this small slope, and the place where this curve would intercept 0 could be way off at like minus 2,000 volts, and you don't care. In this region that you do care about, it has the desired offset, and its slope is very small. So that's the kind of neat thing about using a current source. You can use the dynamic resistance of the current source, whereas with the resistor, you know that the IV curve of the resistor has to go through, the voltage across the resistor is 0 volts when the current through the resistor is 0 volts, which implies that if you want this to be at 0 volts, and if you want this current to be a milliamp, and if you want this slope to be the reciprocal of 2 mega ohms, then you have to put this way down here at minus 2,000 volts, and that would be incredibly inconvenient. But with the current source, it's not inconvenient. You can have that tiny slope, the reciprocal of 2 mega ohms, and yet you can still have this voltage difference be a convenient 9 volts. So that's the beauty of using a current source there. Whoa, okay, that was a lot of stuff. So we don't know in this course how to derive this result. I went to this Georgia Tech electronics course website. I took their incredibly complicated formula and I boiled it down to the essential parts. And I think these parts make sense. So there's this feature of the transistor called the early voltage, which I kind of alluded to at some point. If you draw these IC versus VCE curves for a transistor, you normally see them for different base current values. And a perfect transistor would have no slope here. This would be completely flat, which would mean that the collector current doesn't change as you change the collector emitter voltage. But a real-life transistor does have some slope here, and if you extrapolate all of these lines out to all these lines, if you extrapolate them, they meet at some point on the VCE axis. And that place where they meet is, you can't see that. They meet at some point on the VCE axis, and that point is called negative the early voltage. So in the case of a 2N3904 transistor, if you extrapolate all of these slopes to where they would meet at VCE equals minus 75 volts. Okay, so this is the early voltage. So it's a transistor parameter. It parameterizes basically the slope of these curves. And so this expression is essentially expressing something about how would the transistor, if used without the feedback effect of this emitter resistor, work. And it is something like this. It's like the early voltage plus VCE over the collector current. But then it's multiplied by this factor, which is much smaller than, much larger than 1, right? Because we want this number to be big, because we want its slope to be small, its reciprocal to be small. So you have this emitter resistor, and then you have this resistance that you see looking up into the emitter. And it's the ratio of those two things. So the bigger you make this emitter resistor, the better a current source you get. Although, at least the better a slope you get here. Although, if you make this resistor too big, then it becomes easier to saturate the transistor as this current goes up, because the collector emitter voltage shrinks more easily. But yeah, and again, we said this is a feedback mechanism because, okay, you have your desired collector current. Now suppose the collector current starts to sneak up above the desired point, then the emitter current also sneaks up, and then the emitter voltage sneaks up. But this hasn't changed much, so it clamps down on VBE. If VBE is smaller, then you know IC is exponentially related to VBE, so that makes IC smaller. So IC gets too big, the VBE clamps down, makes it smaller. And if IC gets too small, VBE gets bigger, which then makes IC bigger. So it's a feedback mechanism. And so the result of that feedback mechanism is that we have taken this left-hand factor, which is like 100 kilo ohms-ish, and we've multiplied it by this factor, which is what, 20-ish. So that's kind of cool. 20, 25-ish. Yeah. So the presence of this emitter resistor is basically what gives us this factor of 20 or 25 improvement here in the reciprocal slope of this curve. Whoa, okay, that was a long digression. Good grief, that was a long digression. Okay, what do we expect now for the common mode gain? So we really didn't change the differential gain. The only thing we could have changed that would affect the differential gain is if we changed the quiescent current through these two transistors, we would have changed little RE a tiny bit. But actually, we picked values that gave us a current source current, which is very close to the current we had before with the tail resistor. So it basically didn't change anything for the differential gain. It basically didn't change little RE. Let me go back and just remind you how we set the current in this current source, and then we'll calculate the change in the differential in the common mode gain. Let me do some erasing here. Okay, so before we had a 10K resistor here. And remember, this is about 0 volts, so this is about minus 7/10 of a volt. So if you just called it minus 1 volt, well, okay, whatever. It's okay, it's minus 7/10 of a volt. This is minus 9. So you have 8.3 volts going through a 10K resistor. 8.3 divided by 10E3. Oh, right, duh. So that was 0.83 milliamps through the tail resistor. Now, instead, I claim we have about 0.8 milliamps. Let's analyze that. So I wanted to pick resistor values that were sort of convenient. This is using one more resistor from your one more transistor from your transistor array. This is pins 6, 7, and 8. So 6, 7, and 8 from your transistor array turn out to be one more transistor in this array from the CA3086 transistor array. I first kind of dreamed up what would be ideal, and then I said, well, what do we really have in the box? And this is a pretty good choice based on what we have in the kit. So if you put the base, okay, so if we use, here's from the base, we have 10 kilo ohms to ground, and we have 2 kilo ohms to minus 9 volts. If you neglect, in the absence of base current, then we get the base voltage is minus 9 volts times 10 over 12, right? Because it's the voltage divider equation. That's 10K divided by 10K plus 2K. So minus 9 volts times 10 twelfths is minus 7.5 volts. So the base voltage in the absence of base current is minus 7.5 volts. Therefore, the emitter voltage would be minus 8.2 volts. It's just a diode drop below that. So therefore, the current flowing here through the emitter would be this voltage minus this voltage divided by this resistance. So that's the emitter voltage minus the fixed voltage down there divided by that resistance. So this voltage difference is 8/10 of a volt, because we go from minus 7.2, minus 8.2 volts, right? Minus 8.2 volts to minus 9. So that's 8/10 of a volt difference divided by 1 kilo ohm is 8/10 of a milliamp. That's the emitter current. If the transistor is active, then the base current is tiny, so the collector current is basically the same as the emitter current. So that's also 8/10 of a milliamp. And I didn't want to call it IC because we've been calling this and this, each one of these IC. So I said, let's call it I-tail, which basically should be twice that IC. So the quiescent collector current here should be about 4/10 of a milliamp, and the quiescent collector current here should be about 4/10 of a milliamp. And then they come together and they flow through this tail, well, through this current source, which is 8/10 of a milliamp. So I wired this up. Oh, wait, one more thing. We expect this then to give us, so this term is now so huge compared to these terms, it's basically the common mode gain should be basically minus RC over 2R tail, which is basically, here let's use a less precise equal sign. That should basically be, what is that, 10 kilo ohms divided by 2 times 2 mega ohms, all right, which is like 10K divided by 4 meg, what is that? So 10E3 divided by 4E6. Really? E3 divided by 4E6. Oh, okay. So that's like 0.003. All right, so it should be kind of like, instead of being, right, before we had it was like minus 0.5, and now it's more like minus 0.003. So we got it down by a factor of 100 or 200. Okay, so we made the common mode gain a lot smaller, and without changing the differential gain. We made it probably like a factor of 100 or 200 smaller without changing the differential gain. Let's see if we really did that. So I built the circuit. Oh, no. I built the circuit here. Okay. And what you see is, so it's the same as before. I removed the tail resistor. There used to be a tail resistor going from this point down to minus 9. Instead, now we go from that point over to pin 8. And pin 8 is up here. So it goes from that point over to pin 8, which is the top right corner of the transistor array. And then from pin 7, which is the emitter, so that's the bottom right corner of the transistor array. From pin 7, we have a 1K resistor down to minus 9. So there you go. From pin 7, you have a 1K resistor down to minus 9 volts. There it is. And then from pin 6, which is the base, that's right next door here, we have two things. We have 10K to ground, that's this guy, and we have 2K to minus 9 volts, and that's this guy. All right. Now we wanted to see that the common mode gain became a lot smaller. So initially I was doing what I had been doing before. Oh, here, now let me show you the waveforms. So the waveforms are over here. Okay, here, I'll try to stand over here. So the waveforms are over here. Oh, I don't think I need this measurement. Let's get rid of this measurement. All right. Initially, I was putting the waveform signal into, this point over here, and this point over here, and this point over here, as I had been before. But I think somehow that didn't quite match things up well enough to get. I think that ended up having a little bit of a differential component, because when I do that, then you see I actually see, well, this scale, the input signal is 1 volt per division, the output signal is 100 millivolts per division. So you can see the common mode gain is something like 1/10. And also, there's another thing you can see, which is not inverted. So the fact that it's not inverted tells you that this is really sneaking in, thinking it's a differential signal. It's not the common mode signal. But anyway, so instead of doing that, I said, well, I guess I don't care if I'm going to blow up this transistor array. I mean, of course I care, but. So we're going to put one of these guys into pin 12. Let's see, 14, 13, 12. And we'll put the other one into pin 9. It's like 8, 9, okay. And, oh, here, let me move this. Let me move this so you can see that. How am I going to do that? There. Right. So one of them I put into pin 12 up here. That's over here. One of them I put into pin 9 over here. So I basically plugged them in directly to the two bases. And then that seemed to get me a much more exactly balanced common mode signal. So when I did that, now I see so the yellow trace here is what I'm sending into each one of these two inputs. And the blue signal is the output. And it looks pretty darn small. So I guess I could make this, let me try 1 millivolt per division. Well, that's ridiculous. Okay, I could try 10 millivolts per division. That's, okay. So you basically don't see much of anything. Yeah. Here, I can go back to 100 millivolts per division. Okay. Meanwhile, you see if I unplug one of them, then you see a huge output. It's so big, yeah, it's an absurdly huge output. Okay, so I think the common mode gain is now tiny. What's our bound on it? Let's see. So I would say, can we say, I guess we expect it to be smaller than 0.01. So 0.01 would be if we put one on 1 volt per division, one on 10 millivolts per division. Yeah, I think you could say it's smaller than 0.01 because if there were a factor of 100 difference in gain, sorry, if the common mode gain were 0.01, then the blue curve would be the same size as the yellow curve. And the blue curve is, in fact, smaller than the yellow curve. So I think that's plausible. So it seems like it's probably smaller than 0.01. So I guess that's good. Okay, then let's check and see if the differential gain is still, it should be on the order of 30, right? So we can just pull one of these things out. Oh, which one should we pull out? Let's pull out the inverting one. So the inverting one is going into pin 12. So let's pull out the inverting one. All right. So now we see that this signal is absolutely ginormous. It's too big. It's still too big. So now let's go back over to WaveGen here. And instead of, oh, that's huge. It's a 4-volt amplitude. So let's try an 0.1 volt amplitude. And we go back over here. Oh, ew. Ah, I think it's so big we get kind of a nonlinear response. So anyway, it seems like that's like 6 volts peak to peak compared with 0.2 volts peak to peak. That's about right, I guess. Let's try to make it a little smaller so it's not so nonlinear in the response. So we'll make this 20 millivolts. And then we go over here. Okay, that seems pretty good. So we'll make this like 100 millivolts per division. So we have 40 millivolts peak to peak input, and the output looks like, what do we see? This is like minus 350 to plus 350 is like 700 millivolts peak to peak. So 700 millivolts peak to peak divided by 40 millivolts peak to peak. Oh, is that? No, that can't be right. 700 millivolts peak to peak. What was the input size? Oh, 40 millivolts peak to peak. Oh, that's interesting. That's funny. That's more like 20, and I was expecting 30. Did I do that math correctly? I think, yeah, 350 times 2 is 700. Gee. Did I make the could I have done something that made the differential gain a little small? I really don't think so. Okay, we could try 50 millivolts amplitude, and here we have 200 millivolts per division. Oh, we could try 500 millivolts per division. See, there's a little bit of a nonlinear response there, but okay, so that's 100 millivolts peak to peak on the input. And it seems like the output is, yeah, it's pretty close to 2 volts peak to peak. So I guess somehow our differential gain is more like 20 now, and I think it was originally 30. That would, why is that? Gee. Yeah, okay. Well, I'm a little puzzled by that. I mean, I don't call it really a super qualitative difference because, okay, the differential gain seems to have mysteriously changed from like a little more than 30 to a little less than 20, but the common mode gain went way, way down. But the differential gain really shouldn't have changed at all. So, yeah, I am kind of confused by that. In any case, I think we succeeded at this lab. So, was there anything else we wanted to do? So we did use Q3 of the transistor array to replace our tail with a simple transistor current source. That was fun. We did make the common mode gain tiny. I don't know what we could have done that would have affected the differential gain. Because we changed this tail current from like 0.82 milliamps to 0.8 milliamps. That's a pretty tiny difference. Okay. Anyway, that is lab 16. The only other thing in lab 16 is there's a repeat of the switch in case you didn't do the switch with lab 15. but I assume you did it with lab 15. Okay, so there we are.